Okay, will do. And you will record, right, Kayla? Got it. Okay, great. So welcome everyone to the virtual HPU talk, uh, faculty talk on the COVID-19 engineering innovations, response to the health crisis. I'm Bob Nakata. I'm assistant engineering professor of innovation. And so I'm jointly appointed between CNCS and COB. And also joining us today as presenters are two of my engineering students, Ernesto Arzala and Alyssa Lawton. So you'll also hear about their design project. So here's the agenda. I'm going to discuss an automated non-invasive ventilator, or NIV as it's sometimes called. And I'll go through the motivation behind why I decided to pursue this project. I'll summarize what the requirements are, talk about my preliminary design, my prototype, as well as future design improvements. And also, someone requested that I talk about negative air pressure rooms, which I'm happy to talk about. The students will be talking about their positive air pressure respirator, or paper, and then we'll open it up for questions at the end. So I was watching Governor Cuomo, the governor of New York, on TV when this outbreaks first started to accelerate in the US, especially in New York City, as we all know. And he kept reiterating that they would need approximately 30,000 ventilators at their peak. And fortunately, it turned out they didn't need quite so many. But one of the things that I remember him saying was that worst comes to worst, they would actually bring in the National Guard soldiers to squeeze what's called a bag valve mask, the manual bag valves that you might have seen on some of these paramedic TV shows. So it occurred to me, why would you want to do that manually when you can automate it? So being an Arduino fan myself, and Arduino is a very popular microcontroller, I thought, why not just automate the thing? So that's what my initial inspiration was for this project. And then as I did more digging, I came to realize that, this is a severe problem, not just because of this pandemic, but it turns out in the third world, most medical facilities don't have ventilators. So there really is a demand or a need for having an alternative to the traditional invasive ventilators, which you may have also seen in the media. Those things typically cost anywhere from $20,000 to $45,000 a piece. Hence, you may have heard about attempts to try to share a single ventilator machine with multiple patients. So what I've done, as I'll present to you here shortly, is I've adapted the bag valve mask, and I've attempted to automate it with my design. The other controversy that I came across while doing my research is that there's been some debate about whether you would even want to use a non-invasive ventilator. And without going into all the details of the differences between a non-invasive and an invasive ventilator, what's been shown, at least in the study and other papers I've read, is that if you are immunosuppressed and you require ventilation, there's an extremely high mortality rate of the order of 90%. Saw another statistic this morning that approximately 90% of the patients that were put on traditional ventilators in New York City hospitals actually did not survive. So, it's a therapy of last resort, but if you don't have it, that number is probably 100%, right? So it's a trade-off. And so in this paper that I'm citing here, they found that there are use cases for the NIV, the non-invasive ventilator, and it could lead to shorter recovery time once you've been weaned off of a full-blown traditional ventilator. So a little bit of ventilator 101 here. What this graph shows is a pressure profile. So the key to note here is that you'll see right here at the curve showing the inspiration phase, which means you're breathing in. It tapers off to a peak. In this case, it's shown at approximately 15 centimeters of pressure in a water column. And then as you breathe out, or as you go through your expiration phase, it declines to a non-zero level, okay? And so here it shows at approximately 5 centimeters And so that's an actual constant pressure that remains to keep your alveoli, which are the smallest sacs in your lungs that do the actual oxygen blood transfer. And so you want to keep those alveoli open so that they don't collapse, which can lead to further respiratory distress. So that level is referred to as EPAP, or expiratory positive air pressure. And the difference between that level and the peak is referred to as the IPAP, or inspiratory positive air pressure. So what I'm showing in this table here is a summary of requirements, design requirements. So what I like to do and what I often teach is this whole process of doing engineering design. You must always capture your requirements, which is what I've done here, practicing what I preach. And as you'll see the students show momentarily for their project, you should also validate these requirements by conducting empathy interviews of your end users. That's another process that I teach that's derived from design thinking. One other comment I want to make here before I quickly walk through the requirements is that the FDA has released an emergency use authorization. And what that means is that they're allowing you to deviate from the traditional FDA 510K medical device certification process. I've gone through that process before. Other companies that I've worked at, it's an extremely long, drawn-out process. It can take usually 12 months, sometimes longer, and it's a very detailed documentation process for obvious reasons. You want to make sure that not only do you have medical efficacy for your device, but also that it's safe. So what I've shown here is a list of requirements, and starting with requirement number 1, you can see that I've got a need for programmable breaths per minute, or respiration rate, as well as programmable tidal volume, how much air you're going to push into the lungs. Another requirement is that you be able to have the bilevel pressure that I just showed you for the IPAP and the EPAP. You also might want to supplement the air that's pumped into the lungs with supplemental oxygen. The other key factor here that I came across was that you want to trigger the machine so that it's in synchronous cycles with the patient's natural breathing rhythm. You don't want to be pumping in the air pressure into the patient's lungs while he's breathing out, for example. And so I came up with the means to address that. Humidity, definitely don't want to dry out your soft tissue in your trachea, so you want to have some level of humidity control. And finally, what I've listed here is a need to be able to monitor the patient's oxygen saturation level, which you can do with these clip-on devices that you might have seen when you visit the doctor. Okay, so here is my block diagram illustrating what pieces comprise this NIV system that I'm developing. So what I'm showing here are the various components in these labeled boxes. I've also annotated them with the requirement number from that table that I just showed you. What I've actually built is shown in light blue here, which I'll briefly explain. And then any future upgrades are in the white boxes. So what you see here is what I described in the requirements table, right? So you have a need for an external oxygen source. You want to be able to regulate how much oxygen is being input into the system using this valve. I came up with this idea of having a reversible fan so that I can actually control with more precision the inspiratory and the expiratory airflow rather than just squeezing the bag valve. And so all of this is controlled with this Arduino microcontroller, which the students have learned how to use in my ENG 2004 and 2005 class. And that drives a mechanical linear actuator, which then compresses this bag valve. And then, of course, the air is then forced into the patient's lungs. But you don't want to do that open loop. You want to monitor what the pressure is that the patient's receiving. You want to also monitor their natural respiratory cycle using this radar sensor, and also monitor their oxygen saturation using the pulse oximeter. So a little bit of old advertising here for a startup that I worked for a number of years ago. So we actually developed an FDA-cleared respiration monitor using radar sensors. So it was a non-contact respiration monitor. And you can see that here. These are the actual devices that held the radar sensors plus the electronics. And there was a graphical user interface display here on an iPad. And so we successfully achieved FDA clearance on one of the products, which would read out the respiration rate of the patient from about 3 to 5 feet away from the patient themselves. So it was a bedside point of care device. And so, like I said, that was a long drawn out FDA clearance process. Okay, so a couple of pictures here, a picture and a video. So this is the bag valve mask seen here. You might recognize that from some of the paramedic 911 shows on TV. And then what I've got here is a stepper motor driving what's called a lead screw or jack screw. It's a threaded shaft that to which I've attached this mechanical plate, which then compresses the bag valve. You can see the Arduino microcontroller here in the lower left. Unfortunately, I discovered too late that this stepper motor doesn't have sufficient torque to compress this bag sufficiently. So what I'm showing in this video here is the unit without the bag valve, but you can see how it's, if the bag valve, if the motor had sufficient torque to compress the bag valve, you can see how this motion is approximately what you would expect in a normal respiration cycle. So approximately 15 breaths per minute is the average respiratory rate. And that's all programmable from this Arduino microcontroller. Okay, so future improvements. So, I like to think that this project could turn into a student engineering design project in the future. But clearly, we need a stronger motor with higher torque. And then adding all of those other components that I showed in my block diagram derived from my requirements table. So adding the external O2 source, the pressure valve, being able to control the IPAP and EPAP, for example, and all those other features that I described. Okay, and I was also asked to talk about a negative air pressure room, which you'll find in many of the ICUs. So what it is a method to isolate the potential harmful virus within the patient's room itself. And the way you do that is you maintain a negative air pressure within the room. And so what's shown here is the patient room here. You've got an external air source that's flowing at a rate of, say, CFM1. CFM stands for cubic feet per minute. That's the parameter for measuring airflow. And within the room itself, you've got another fan that's ventilating an exhaust from the room at a different CFM rate, CFM2, which is greater than the input CFM rate. So the result of that is that you'll have a negative pressure gradient. So the surrounding air pressure is greater than the air pressure within the room itself. That way the virus is contained within that room. Of course, you'd want to make sure you've got HEPA filters, high efficiency particulate filters here so that you're filtering out the virus. Okay, and just as a quick introduction to the student project that you'll hear next is the motivation for the paper or the positive air pressure respirator. So, with watching all of these point of care first responders wearing the traditional face mask, or the face shield, I should say, it occurred to me that, the bottom of that mask, I don't know if you can see it in this photo here, is open. So if they're in an environment where the virus has been aerosolized, even though they're wearing an N95 mask, the virus can still enter their eyes. Their eyes are not protected usually. And I'd say, half the time I see the news, that's exactly the case. They're not wearing shielded goggles over their eyes. So there's no protection whatsoever to the eyes in this traditional face shield. And it turns out that I've did some research on the aerosolization risk. During the intubation, extubation process, when they're removing the ventilator pipe from the trachea, that's when aerosolization predominantly can occur. And according to this paper cited by from the CDC that I cite below, it could actually, propagate as far as 4 meters or even farther if there happens to be, some type of air current within the room, or for that matter, even outdoors. And according to another paper published by the New England Journal of Medicine, they discovered that the virus can in fact remain aerosolized for, as long as 3 hours or even longer if you look at this curve. So that's a pretty scary statistic. And so I'm actually quite surprised that the doctors and nurses aren't wearing the full-fledged face masks. And so that was kind of the motivation or the inspiration for the next project, which Ernesto and Alyssa will present. Okay, so are there any specific questions for my part of the talk? Maybe I should address those now before we move on to the students. Okay, I'm open to questions at the end as well. All right, so with that, let me turn it over to Ernesto and Alyssa. They are both students in my ENGE 2004 microprocessors and digital electronics class, and they're also in the lab, which is the ENGE 2005 class. Okay, go ahead, Alyssa. Let me stop sharing the screen, I guess.
Yes, that would help.
Yeah, stand by.
Okay, so.
1 second, I'm trying to unshare. It's not letting me do
the
it.
sharing.
Did it? Okay.
Yeah.
Is
All right.
everyone able to see my screen now?
Yes.
Yes.
Okay.
Yes.
I just want to double check. Ernesto, are you ready?
Yes, I am.
Okay. Well, good afternoon, everyone. As Dr. Nakata mentioned, my name is Alyssa and my partner's name is Ernesto. And the project we selected for our digital hardware and microcontrollers course is the positive air pressure respirator. As we all know, COVID-19 is a prevalent pandemic that we are still finding new information on as of today. According to the Center for Disease Control and Prevention, COVID-19 transmits through a droplet form that enters an individual's mouth, eye, or nose and can be inhaled in one's lung. To protect one's eyes, face, and respiratory system, personal protective equipment, also referred to as PPE, dictates that we use equipment such as face shields, masks, and goggles in a contaminated environment. Even when using a combination of a face mask and face shield, particles have the ability to infiltrate any gaps. Since the virus can be aerosolized, as Dr. Nakata mentioned, our eyes are exposed to these contaminants when not wearing protective goggles. After conducting interviews, we came to the conclusion that PPE is not satisfying the expectations to protect individuals against this pandemic disease. Now, interviews were conducted with a pool of 21 people who are either medical professionals, frontline workers, or are currently unemployed due to the coronavirus. We've selected a few questions from our interviews that we felt were most pertinent to our project. Our first selected question states, what issues do you experience when using face masks? Almost half of those who expressed discomfort when using a face mask described they experienced either claustrophobia, difficulty in breathing through a mask, bruising along the bridge of their nose while using masks such as the N95, irritation due to heat, fogging when wearing glasses, and an inability to secure the mask to their face. The second question we selected states, what would help you feel safer in your work environment? Over half stated they would either feel safer if there was an improvement in PPE and a larger supply of this equipment. Under a quarter felt it would be a better option to social distance from one another by utilizing programs such as telehealth. This, of course, is not an option for our first responders who are caring for these patients. And lastly, we asked, do you feel it is necessary to wear a full body pressure suit? Why or why not? Some of these people stated they felt a suit was over excessive, while others argued that, depending on the location, they would feel it would be safer wearing one. Majority felt it was unnecessary to wear a full body suit, which guided our decision to focus on a full face mask respirator. So this here is a system block diagram of the PAPR. Starting from the left, we used an air supply unit, in our case a CPAP machine, that contained a HEPA filter and connected to a full face scuba mask. Attached within the scuba mask was a BMP 180 pressure sensor and LED lights. Another pressure sensor was located outside of the mask and connected to an Arduino Uno that processed the data and outputted the feedback to a liquid crystal display screen and LED lights. Now, the full face scuba mask was used to block all main entries of the virus, as it is tightly secured due to the face piece feature. In order to monitor the difference in pressure, the BMP 180 sensors collected instantaneous readings that were processed by the microcontroller. The CPAP machine provided the air supply for the purpose of our experiment, but we intend on using a separate air supply unit. LED lights were placed in the mask near the eye level to inform whether the pressure in the mask was positive or negative. And lastly, the LCD screen displays the calculated difference of the pressure. And now, Ernesto will be providing you with further details of the components we selected.
All right, thank you so much, Alyssa. So there are 4 main components in the monitoring system, and those include the Arduino Uno that computes the information from the sensors and activates the monitoring system. The pressure sensors that are pictured on the left that are measuring the pressure levels inside and outside of the mask, and the liquid crystal display that shows the real-time pressure differences between the 2 sensors. Finally, our LED monitoring system that is shown on the right that is fitted within the mask to show that the user, if the system is working properly. All right. Next is going to be a picture that shows what the entire assembly looks like. As you can see there, the air is supplied by a CPAP machine, because the CPAP machine can assure a nice continuous flow of air that is going to be supplied to the mask, and it's also going to assure that it stays clean for me. Next, we're going to be showing you a video demonstration of what the whole system is going to be working like. All right. All right, as you can see, I'm putting on the mask right now, and that the red LED light is blinking. It's blinking right now because there's no air being supplied in through the CPAP. So it'll soon turn into green. As the green LED light turns on, as you can see on the LCD screen, that positive pressure difference is going to be displayed on that LCD screen. And then as soon as I turn it off, the LED will turn red and begin to blink to show that the user that the air supply is turned off, as there's some reason or there's some other problem with the system. All right, now I'm going to demonstrate what happens when the mask is going to exhibit a seal breakage or of some sort. So I peel off the mask slightly off of my face, and then the system shows that there's a problem with the system. The LED lights will turn red, and then I'll seal it back up, and then it'll turn green once again. And that is how our system works. So here are some of the future advancements that we're looking forward to do with this project. First is a PC fan to make the system a little bit more affordable, and a 3D printed assembly to house that fan, as well as an N95 filter, so we can assure that the air that's being supplied by that PC fan is nice and clean. Next is hiding all the wires and making the system safer to be used in most environments, like moist environments and such. Having the system run remotely with its own power supply rather than keeping it connected to my laptop or an outlet. A waist belt attachment for more portability, introducing other methods of air supply such as ventilators, and an audio system since there's difficulty of projecting the voice with the mask on. User application for control and monitoring of the system. And next we'll be showing you what the 3D rendering will look like with the PC fan implementation. All right, is there any questions?
I guess we did such a great job. There's no questions.
Looks good.
Let's see who's there in the audience. I recognize John. John, do you have any questions?
Not off the top of my head, but
what other projects could other students like myself potentially help you guys out, either for the next month or possibly during the summer?
Yeah, so I think both of these, as you just saw, require additional work to improve upon. So if you're interested in, helping out, pitching in with either, that'd be great. And keeping in mind that in the fall, if you're a third-year student, there are design project requirements in your program plan. So, you could potentially turn one of these projects into that to satisfy that course requirement. So really, whatever you can come up with to help address, these issues that are being confronted by our medical care workers, whether it's PPE or some other engineering solution that needs to be done. This all started from when I joined the COVID-19 working group for HPU about a month or so ago, and as you may know, there's been a big initiative, a big push to 3D print the headbands that hold the face shields, right? And so if you've got any 3D printing expertise, that would be helpful. But as I said, in my introduction to the paper project, I think the issue with those face shields is that it has an open bottom. So I think that puts the point of care individual at risk. So yeah, it's really whatever you can think of to help address this pandemic.
Okay, thank you.
I see that there's a question that was geared towards us in the chat. It says, just wondering how many people we were interviewing and if those people were in a particular group. I'll go ahead and send that to Alyssa. She mentioned that in that part of the presentation.
Okay, well, as I mentioned, we only did a group of 21 since, of course, we were limited to time and the amount of people we could reach out to, especially in this time of quarantine. Our first targeted group of people was, of course, our first responders, so anyone in the medical field. And then if we could get any other people from different experiences and backgrounds, such as people who were unemployed or frontline workers, that was also who we were targeting as well. Did that answer your question?
Yeah, so what I had both Alyssa and Ernesto do there, as well as with the other students in the class, is to do what's called market validation and customer discovery. This is part of the lean startup methodology and also part of the design thinking process that I mentioned. And so you want to do that for any engineering project that you pursue. And so that pretty much ensures that whatever you design is going to satisfy the needs of the end user, and you're not building something that, that they're not going to buy or not going to use. Any other questions? Not sure who the other members of the audience are. I don't recognize the names here. I do recognize Dr. Crawford. Do you have any questions for us?
No, things look pretty good from my perspective. Good presentations on all your parts. Thank you.
Thank you.
Thank you. Actually, this is the reason why I've been pinging you about expertise in your student population. Anyone that's got expertise with Arduino or iOS application programming could potentially build the user interfaces for both of these devices. You could even put it onto a phone and have an app that you could then use to control, the various settings for the non-invasive ventilator, and obviously for the positive air pressure respirator as well. Okay, Kayla, I think that concludes our presentation.